Quantum tunneling is a fascinating process in which a particle goes through a barrier that it shouldn't be able to cross in seemingly no time, breaking the speed of light limit. Or maybe not. Physicists have argued about just what goes on in quantum tunneling for a century. It seems like the kind of esoteric quantum problem that'll never be answered, but just last week, the situation changed. Tunneling is one of these weird things that can happen in the quantum world, but that's totally at odds with our everyday experience. If you hit your head against a wall, it'll either go through or it won't. If your head was a quantum particle, it would always have a chance of it going through. Tunneling can happen whenever you have a quantum particle that faces a barrier which takes energy to overcome. This could be, for example, because a particle is trapped by some kind of attractive force. You could imagine it being gravity, but it could be anything. The particle needs a certain amount of energy to escape that trap. Also, it seems. Because if you take a quantum particle, it can get out of the trap even if it doesn't have the necessary energy. Basically, it takes the energy from nowhere, escapes, and then hands the energy back to nowhere, so that energy conservation is fulfilled. This sounds crazy, but quantum tunneling is a real and measurable effect. It's what scanning tunneling microscopes are based on, and it plays an important role for nuclear fusion, where particles face such a barrier. Nuclei are all positively charged, so if one approaches the other, it'll be repelled by the electric force. However, the strong nuclear force is attractive. It only becomes relevant at short distances between the nuclei. If you add these forces together, that creates a potential barrier. That nuclei can tunnel through this barrier is why fusion in our sun works. The tunneling effect is not difficult to calculate. You can see here what happens if you take a particle that's localized to a sort of lump initially and then let it hit an energy barrier. This energy barrier which you see here isn't a real wall. It's just some sort of obstacle that takes energy to overcome, like the previously mentioned repulsive force. You can see that if the quantum particle hits the wall, most of it is reflected, but some of it goes through. That's the tunneling. But what's this shape that I've drawn here? This isn't the actual particle, it's the probability to find the particle, because that's how quantum mechanics works. So what the mathematics tells us is that any one particle has a certain probability of just going through the wall. The weird thing is now this: if you compare the speed of the particle that goes through the wall with one that never encounters the wall, then it seems like the one which went through the wall will, on average, be faster, because the average is where the bump of this distribution is. If the particle was a quantum of light, then that means it must have been faster than light. This isn't a joke. There have actually been experiments where they measured this, or at least it's what they think they measured. You see, the problem is that you can't really tell how long the particle took to travel because you don't know exactly where the particle came from. Maybe the particles that arrived sooner were just the ones that left earlier. Very confusing. Now comes this new paper with a very clever idea. You'll love it. They say, look, the key feature of quantum mechanics is that all particles are also waves. This means, among other things, that they have an internal clock, because waves wave. They change periodically, like a clock. Now, you can't actually measure this waving for one single particle, but you can measure the difference between two particles. This is how interferometers work. So they say in the paper, what they'll do is to create pairs of atoms that start out being synchronized in their waving, so to speak. Let one run into the wall and the other one past it, and then compare the results. That should allow them to figure out what's actually going on. Does the particle kind of jump through the barrier with no time passing, or do they both move at the same speed, just that one takes the forbidden path, so to speak? They haven't actually done the experiment yet. The paper just explains how it would work. But they say it's feasible with current technology, so hopefully someone will do this experiment in the near future. And this might actually settle a 100 years old debate. Progress is truly unstoppable. Who knows? Maybe we'll one day actually find out whether it's okay to put pineapple on pizza. Last week, I saw a lot of headlines about a space propulsion system that uses nuclear fusion. Nuclear fusion in space. Very cool. Let's have a look. So the news comes from a company by name Rocketstar Inc., which announced in a press release that they have reinvented spacecraft by releasing the world's first fusion-enhanced space thruster, the Firestar TM fusion drive. They claim that the Firestar TM fusion drive improves their water-powered pulsed plasma thruster by harnessing aneutronic nuclear fusion by 50%. Let's try and sort out the technical mumbo-jumbo, starting with the basics. What's a thruster? A thruster is a device that generates thrust, which is what rocket scientists call a force. Yes, that's just mass times acceleration, good old Isaac Newton. The unit of thrust is also called Newton. Sorry, Albert. In space, the only way we know to generate thrust is throwing stuff out of the spacecraft. You throw things out one way, and since action equals reaction, the spacecraft will go the other way. Yes, that's Newton again. The warp drive guy seems to want to get around this somehow, but I can't really see that working out. In a normal rocket, you throw out fuel as quickly as possible. The thrust you need to shoot something into space from Earth's surface depends on the size of the thing you're trying to get off the planet. But for a typical NASA rocket, it's in the ballpark of 40 million Newton or so for the first stage. That's a lot, and is why space travel is so difficult and also expensive. A plasma thruster now is a different propulsion method, though it works by the same basic principle, namely throwing stuff out. In this case, you take some sort of gas and make a plasma out of it by electric sparks. That the gas becomes a plasma means that the electrons float around freely and are no longer bound to the atoms. Once you have the plasma, you can separate that into positive and negative charges, accelerate them with electric and magnetic fields, and then throw them out of the spacecraft. Plasma thrusters do exist. In one of the most widely used ones, the gas comes from evaporating Teflon. The nice thing about plasma thrusters is that they're very energy efficient. This is because with the electric and magnetic fields, you can convert a big part of the energy into directed motion of your fuel, that's the plasma. Chemical propellants are far less efficient. The downside of plasma thrusters is that they produce very little thrust. We're typically speaking about a few millinewton. You can't use these thrusters to get anything off the planet. However, once you're in space, you need very little thrust to move a spacecraft. Suppose you have a satellite in orbit or a telescope at its intended location. The only thing you need to do then is minor corrections. And then what matters isn't lots of thrust, but that the energy source survives for a long time. Plasma thrusters are really good at that. Okay, so that explains the thruster and the plasma. Now, this new company has been using plasma created just from water. Water has a fairly low density, so that sounds not so great. On the other hand, some amounts of water have been found on the moon and on some asteroids, and it could be something that a spacecraft can actually refuel, which is hard to do with Teflon, unless possibly an alien pan dealer comes your way. And that it's pulsed means what you think it means. They shoot the stuff out in pulses. That's probably more efficient than doing it continuously because you don't want the ions to get in the way of each other as you accelerate them. Now the thing with the fusion. If you ionize water, you don't just get H2O ions. Ripping off the electrons tends to destabilize the entire molecule, so it often falls apart into an HO and an H, which is just a proton. These guys now shoot with a boron beam at the protons. The boron nucleus can capture the proton, which creates a carbon isotope that's unstable and decays into several helium nuclei. The point of doing this is that the binding energy of carbon is lower than that of boron, so that process releases energy. Among the elements that you can fuse with a proton, boron has the second lowest energy threshold for a fusion process that does not release a neutron. This is why it's called aneutronic. That's nice because neutron radiation is really nasty and rapidly degrades materials. This is also why boron fusion would be much preferable for fusion reactors. However, getting boron to fuse with hydrogen requires much higher temperatures than the more commonly pursued deuterium-tritium fusion, so very few groups work on that. In any case, these guys now say, hey, we inject the boron into the plasma. The boron fuses with some of the protons. That creates carbon, which decays, and we get an extra kick. They say they've measured the decay products, so they know that the fusion actually happens. Their press release says it's increased the thrust by 50%. That brings them to maybe 24 millinewton. They're planning to launch their propulsion system into space with the SpaceX rocket in July to see how it performs. And that's all well and good, but I think the key question is how much energy they had to use to arrive at that increase in thrust. Unfortunately, the press release doesn't say anything about it. I'm somewhat skeptical it's energy efficient, because if it was, why aren't they just producing energy with boron fusion? You might find 24 millinewton a bit disappointing, so let me not withhold from you that engineers have totally made conceptual plans for powering rockets for good with nuclear fusion or fission. The most famous example is maybe the Project Orion, that was based on the idea of detonating small nuclear bombs behind the spacecraft and then riding on the shock waves. The concept was abandoned in the 1960s, though the idea of riding on shock waves later became the founding principle of social media. If that isn't quite your thing, you can use pretty much any nuclear fusion reactor as a propulsion device, because they generate fast charged particles that you can throw out one end of the rocket and off you go. That could generate a lot of thrust from very little fuel, which is ideal for space travel. And yes, that means that every company which is working on nuclear fusion reactors is basically also working on a rocket propulsion system, though it'd work better for smaller devices. That said, I'm wondering now, why does Einstein not have a unit named after him? I'd like to propose we use the Einstein as a unit of ingenuity. I'll give fusion-enhanced plasma thrusters 0.1 Einstein. Not a bad start, but more work is needed. Last week, I saw some scary headlines. The many worlds interpretation now has many more worlds, they said. The infinite multiverse could be infinitely bigger. No one needs that, I thought. But I had a look at the paper, and it turned out to be not remotely as bad as the headlines made me think. Indeed, I very much welcome this paper. Well, at least I do in this universe. Let's have a look. You've probably heard a lot about how quantum mechanics is supposedly strange and impossible to understand. But I think there's really only one problem with quantum mechanics. No, it's not that the German word quantum also means stinky feet. It's that quantum mechanics doesn't describe the world that we actually experience, or at least the one that I experience, because for all I know, you don't exist. In my experience, tables are either in one place or another, but not in several places at the same time. Cats are either dead or alive, but not both. I either talk or I don't talk, but you can usually tell which. Things have definite properties. In quantum mechanics, in contrast, objects don't have definite properties until you measure them. Quantum mechanics tells you that it makes no sense to ask whether the cat is dead or alive, or where a particle is, until you've made a measurement. That's what makes quantum mechanics strange. Physicists call the non-quantum world with definite properties classical. The problem with quantum mechanics is the emergence of the classical world. It just doesn't come out of the maths. It's not there. This is why quantum mechanics has this clumsy fix that's called the measurement postulate. The measurement postulate just says Okay, but whenever we look, they do have definite properties. The issue with the measurement postulate is that we don't actually know what a measurement is. Okay, it's an interaction with a measurement apparatus, but then what's a measurement apparatus? In a paper that I continue to find hilarious, a bunch of physicists assumed a single photon can be a measurement apparatus and concluded that therefore reality doesn't exist. You would have thought that this is the ultimate reductio ad absurdum, but no, they seem to actually believe that this means reality doesn't exist. The new paper works kind of like that too. To be fair, physicists have not just twiddled thumbs in the past century, they have tried to explain what a measurement is with an idea called decoherence. Decoherence is the loss of coherence that happens when you interact too much with your environment. That is true for particles as well as for parties. But for particles, the environment is typically air or vibrations or light or even the cosmic background radiation. A quantum object that has decohered still doesn't have definite properties, so that doesn't really solve the problem. But the thing is that once you have specified what a measurement apparatus is and what the environment is, you can identify some properties of the measurement apparatus that don't decohere. They're in some sense stable. So the idea is that you say these stable states are the ones that we can measure. This is called environmental selection, or Einselection for short. The problem is that to even make use of this, you already have to specify which part the measurement apparatus is and what part the environment is. A decade ago or so, I thought about this longer than I probably should have and arrived at the conclusion that Einselection can't solve the measurement problem. The funny thing about the new paper is now that they asked the same question as I did, got the same answer, namely that it's not possible, but drew a completely different conclusion. You see, what they did in the paper is that they generated some simple examples of systems that can represent the measurement apparatus plus its environment. And then they ask, if we just try out all possible divisions into two parts, do we find one that's special so that we can identify the measurement apparatus as the one part and the other as the environment? Their answer is no. This procedure would allow many more things as measurement devices than we observe. But where I said, well, this means that this method doesn't explain what we observe, they say, since this doesn't explain what we observe, there must be other universes in which other beings measure all those other things. And that's where the headlines come from, because now you have many more worlds than even the many worlds interpretation has, because now you have many more things that count as measurement apparatuses. This is the exact same mistake that all multiverse fanatics make. Because their maths can't explain why the world is as we observe, they postulate that all their maths must be real, rather than concluding that maybe there's something not quite right with their maths. Still, I'm thrilled about this paper, because you see, I'm convinced that the next breakthrough in physics will come from figuring out just what a measurement is. And trust me, that'll be a little more practical progress than debating whether reality exists. The bird flu has spread to cattle in the United States. Inactive fragments of the virus have been found in milk. The World Health Organization rates the current risk for humans as low, but epidemiologists all over the world are on high alert. I have the summary. The avian influenza, commonly known as bird flu, comes in many strains. The strain of the current outbreak is H5N1. It was first isolated in farmed geese in China in 1996. Wild birds have since spread it all over the world. Among birds, it has a fatality rate exceeding 90% within 48 hours. That's bad for the birds, but good for us, because it means that outbreaks are discovered very quickly and contaminated poultry is very unlikely to enter the food chain. The variant that currently concerns researchers has the number 2344B, just so you've seen it in case someone asks you on the street tomorrow. This variant was first documented in October 2020 in the Netherlands. Within a few months, it had spread across Europe and to Africa, Asia and America. In recent years, there have been numerous reports that this variant has infected mammals, including otters, foxes, bears, minks, cats, and now cattle herds in the United States. This new outbreak began in March. By last week, the virus had spread to more than 36 herds in 8 states. Genetic analysis suggests the outbreak likely originated from a single spillover event from birds, and the virus then spread between cattle herds. This is bad news. The H5N1 virus is known to be able to also infect humans. The World Health Organization has counted about 900 cases of infected humans from 2003 to 2024. About 50% of the infected people died. However, these numbers are for earlier variants of the strain, not the current one. So while a 50% case fatality rate sounds alarming, there's no reason to think that the variant which is currently circulating would be that fatal. Indeed, for the current outbreak in the US, there has so far only been one reported case of an infection in humans, a dairy farm worker in Texas. He had mild symptoms and seems to have recovered well. However, scientists suspect that more people have been infected, just that no one noticed. The World Health Organization says that there are no virus sequences from dairy cattle in the USA that have well-recognized markers of mammalian adaptation. So again, no reason for alarm. Still, this appears to be the first time this virus has managed to spread widely among cattle, which is clearly not good. The American Food and Drug Administration, FDA for short, has further reported that they took samples of pasteurized milk and analyzed it for traces of the virus. Pasteurized milk is the one you usually buy in the supermarket, which has been heated to avoid microbial contamination. The FDA found inactive fragments of the virus in 1 out of 5 milk samples. They later also tested other dairy products, such as cottage cheese and sour cream, with similar results. Virus fragments, but no live viruses. These fragments cannot lead to infections, but the FDA advises strongly that if you live in the United States, that you avoid raw milk and do not give it to your cats either. Epidemiologist Eric Feigl-Ding says that at the moment he wouldn't even touch pasteurized milk because he believes viruses could survive inside of fat droplets in the milk. He sticks with ultra-pasteurized milk that is heated more. The FDA also tested infant formula and powdered milk but didn't find any traces of the virus. The World Health Organization assesses the current risk for humans as low, but says that the situation requires real-time monitoring. This basically means they think it could get worse very quickly. There's no documented case of human-to-human transmission with the current variant. However, there have been reports of human-to-human transmissions with earlier variants of the H5N1 virus. And yes, there are vaccines against the bird flu, both for birds as well as humans. Some of the vaccines for humans have been approved for use in the United States and in the European Union. However, since the vaccines would have to be adapted to a particular variant in an emergency situation, no one sits on huge stockpiles. So vaccines would have to be mass-produced very quickly should the need arise. It's unclear how well the vaccines work in humans because infections are so incredibly rare that there's no data. That the bird flu jumps over to humans is a disaster waiting to happen. It's not a question of whether it'll happen, but just when. There's a real risk that this is the start of the next global pandemic. Or maybe we'll get lucky and it'll take a few more years, but the next pandemic will come, and birds are a very likely source. Indeed, scientists think that the Spanish flu pandemic of 1918 was caused by a mutation of a bird flu virus. It's not the kind of thing that I normally talk about, and part of me feels like I shouldn't touch the topic. Then again, it's a situation that can rapidly get worse, and I think I have somewhat of a responsibility here to keep you informed. Or maybe I'm just a shill for the soy milk industry.